We have discussed in very detail in the few previous videos the problems of free oscillator and the damped harmonic oscillator with 1 degree of freedom. And after the completion of the concept of free oscillation and the damped harmonic oscillation, in the last lecture, just we have started to deal with a very important problem of forced harmonic oscillations. Okay, so we have already completed our first lecture on forced harmonic oscillations, and in that very lecture you have seen uh, the basic concept of forced harmonic oscillations. Actually, you have seen in that lecture how these forced harmonic oscillations differ from the free oscillation and the damped harmonic oscillation. Actually, in case of the damped harmonic oscillation, a resistive force or a damping force acts on our system, that is oscillator. And due to that damping force, actually the energy of the oscillator gets lost, and so that its amplitude decreases exponentially with time, and finally it becomes zero. And so that after some time the oscillation gets stopped. But now the problem arises, if our aim is to maintain the oscillation of the oscillator, how we can do? We have seen in the first part of this lecture that for this we have to apply a periodically varying force, that is a force which varies periodically or harmonically with time. If such a force is applied on the oscillator, then that applied force or that external agency compensates the energy loss. It means that provides the energy to the oscillator, and so that the oscillator in course of time is completely governed by that applied force and oscillates just like a free oscillator. All these things we have discussed in the first lecture on these forced harmonic oscillations. And considering the three forces acting on our oscillator, we have set up the equation of motion. And you have seen actually the equation of motion of forced harmonic oscillations have two solutions. The first solution is known as the transient term or the complementary function. Actually, in this case, the oscillator just behaves as a damped harmonic oscillator, and but that damped harmonic oscillation dies out very soon, and after that our system is in a steady state. And when the system is in a steady state, then it is completely governed by the applied periodic force and oscillates with a constant amplitude just like a free oscillator under the applied force. That state is called a steady state. Actually, aim of this second part of the lecture is to discuss that a steady state solution of the equation of motion of the forced harmonic oscillator. Okay, we have already discussed the solution of the transient state of the oscillator in the first part of the lecture. So you can see I have mentioned here all the important results which we have discussed in the first lecture on this forced harmonic oscillation. You have seen that the equation of motion, this EOM stands for equation of motion. Under this periodic force, which is F naught e to the power I omega t, this equation of motion is given as m times d2x by dt square plus r dx by dt plus kx equal to F naught e to the power I omega t. Okay, here actually this x is equal to x of t, So this is also a problem of 1 degree of freedom, because this dependent variable x is a function of only one independent variable time t. So this is also a problem of forced harmonic oscillation with 1 degree of freedom. Okay, so this was the original equation of motion in this case. But when you have discussed in the first part of the lecture the transient state of the system, then we consider that our system is independent of this applied force in the very beginning of its motion. And so the equation of motion for transient state of our system is simply written by taking this force term equal to 0. And you have obtained that the equation of motion for transient state is given as d2x by dt square plus 2b dx by dt plus omega naught square x equal to 0, where this 2b has been written for r by m, where r is a resistive constant which depends on the nature of the medium. And this b, this is called damping coefficient of the medium. And this omega naught square has been written at the place of k by m. All these things you have studied previously. And this omega naught is actually called the natural frequency of our oscillator. Okay. And when we have solved this very equation, then you have seen in the first part of the lecture that the solution of this equation of motion in transient state is known as complementary function or the transient term. And that very transient term or the complementary function is given like this. This is x of t is equal to x1. I have written the first solution by the symbol x1. The second solution will be written by x2. And it was found that this is a naught times e to the power minus bt times sine omega prime t plus phi. Here actually this omega prime is equal to a square root of omega naught square minus b square. Okay, this is the frequency with which this damped harmonic oscillation takes place, and you can see it is slightly less than the natural frequency omega naught. So up to this very point, everything we have discussed in the first lecture on this damped harmonic oscillation. Okay. Now in the second part, our aim is to find the steady state solution of the equation of motion of the damped harmonic oscillations. Okay. In fact, when you say steady state, what does it mean? It means, as I have told you earlier, that you can see this solution x1 which contains the factor e to the power minus bt. Actually this x1 decays exponentially with time. Okay, due to the presence of this sine function, oscillation takes place, but its amplitude is exponentially decaying. So this oscillation will not continue for a long time. It will vanish, it will cease. When the transient term vanishes, that is x1 becomes 0, actually after that our system oscillates under the applied periodic force with the frequency which is equal to the frequency of the applied force. Okay. And so if your aim is to find the steady state solution of the equation of motion, you can't take this term f naught e to the power I omega t 0. You can't take. You have to consider it. Okay. Actually, in this condition, the solution of the equation of motion is called a steady state term, or it is also called particular integral. Okay. And as I have told you that this actually describes the behavior of the oscillator after transient term has died away. Okay, and I have just told you that in a steady state the system is completely governed by the applied force, and so that you can say in this condition the system oscillates with a frequency which is equal to the frequency of the applied force, just like an undamped Frey harmonic oscillator. Okay, so now we will solve the equation of motion in case of steady state of the system. Okay, and you have seen that this equation of motion is given like this. This is m time d2x of t by dt square plus r dx of t by dt plus k times x of t, and that is equal to f naught e to the power I omega t. Okay, actually the force governs the motion of the system. So what will be the nature of motion, what type of motion our system will perform, that is completely decided decided by the force under which the motion is taking place. And you can see here actually the motion is taking place now under this periodically varying force. So we can guess that this force will provide a motion to the system just in accordance with its own nature. So you can say that the motion of the oscillator will be also periodic, also oscillatory. Okay, and hence you can take a particular solution of this equation 1 in this form, that is x of t equal to a times e to the power I omega t. You can see here actually x is the displacement of our system from its equilibrium position, and this factor e to the power I omega t, this is just a oscillatory quantity. So this solution actually indicates that the system will oscillate with the frequency omega, which is actually the frequency of the applied force. So x of t is equal to a to the power a e to the power I omega t. I have taken this just as a solution of this equation 1. You can also say that this is just a trial method. We guess that the motion will be just in accordance with the nature of the force. Okay. Now we have defined x of t, but our equation of motion consists not only x of t, but it also consists of the first order derivative of x and the second order derivative of x with respect to t. So now let us find first of all these two derivatives, and after getting the values of these two derivatives we will simply substitute all those values in this equation 1. Okay, so you can see x of t is equal to a times e to the power I omega t. So you can easily say what will be dx by dt. This is a simple differentiation. You can see this dx by dt will be equal to I omega times a e to the power I omega t. Okay, and d2x by dt square, again differentiate it. So this factor I omega will be outside, and I times I, this will be I square, and that is equal to minus 1. And so that d2x by dt square is simply equal to minus omega square a e to the power I omega t. Okay. Now let us substitute the value of x of t, value of dx by dt, and value of d2x by dt square in this equation number 1. Okay. You can see when we will substitute all these values, this factor a, which is just a complex quantity, this will be present in all the three terms in LHS. And similarly, this e to the power I omega t, this factor will be also present in all the three terms in LHS. So we can take this A times e to the power I omega t as a common factor. Okay, although A has been written in left side and e to the power I omega t has been written in right side for convenience. Okay, so taking A times e to the power I omega t, what will be the LHS of this equation 1? You can see this will be A times minus omega square m plus I omega r plus k times e to the power I omega t, and that is equal to f naught e to the power I omega t. Okay. Now you can see this e to the power I omega t will cancel out because it is present in both sides, and so we can now find this amplitude A, which is in general a complex quantity as I have told you earlier, and now you can see it. So A will be what? This will be this much. This is f naught over minus omega square m plus I omega r plus k. Okay. Now let us simplify this result to some extent. This can be written as f naught over, we will take this I omega as a common factor in denominator. Okay, I omega. So when we will take I omega as a common factor, the remaining terms will be what? This will be r minus omega m over I plus k over I omega. It is okay? Now see, you know this 1 over I, you know this is equal to minus I. Definitely you have an idea of it. Okay. So for 1 over I have written here minus I, you can see. And so A is equal to minus I f naught divided by omega times r plus I omega m, because here again for this 1 over I we will write minus I, but minus is already present here, so the second term becomes plus I omega m, and in the third term there is 1 over I which is minus I, so this can be written as minus ik over omega. Okay. Now this these last two terms contains I, so let us take I as a common factor, and so you can write A is equal to this much. This is minus I f naught over omega times r plus I omega m minus k over omega. Okay. Now for this bracketed quantity you can see, which is just a complex quantity, r is its real part and omega m minus k by omega is its imaginary part. Okay. And for this I have written here Zm. Actually over this Zm I have put the vector sign because a complex quantity is just equivalent to a vector. Okay. So A can be written as minus I f naught over omega Zm, where I have told you that this Zm is equal to r plus I times omega m minus k over omega. Okay. Actually this Zm is called the complex mechanical impedance. In fact, if you have studied the LCR circuit in your course on electricity, particularly in the chapter alternating current, then you have seen that actually in case of LCR circuit, the complex impedance Z is given by R plus I omega L minus 1 over omega C. This is actually the electrical impedance. Okay. So comparing with this result, we say that this quantity Zm equal to R plus I omega m minus k by omega, this is actually the mechanical impedance of our system. Okay, mechanical impedance. And we can represent this Zm in a vector diagram or in an Argand plane. You can see if we take this xx dashed axis as the real axis and this yy prime as an imaginary axis. This is imaginary axis. Okay. Then the real part will be along this x-axis, which is r, and its imaginary part, which is omega m minus k by omega, which I have written here xm. Actually, this xm is called reactance. This is called reactance. This is mechanical reactance. xm, this is mechanical reactance. Mechanical reactance. Sorry. Okay, mechanical reactance. So if you represent vectorially this xm is actually omega m minus k by omega, and since it is multiplied by I, and you know I just acts like an operator which rotates the vector by 90 degree, so this xm will be just in a direction perpendicular to this r. So this is along the imaginary axis. Okay. And from triangle law of addition, you know this vector OP plus PQ, this will be equal to what? This is equal to OQ. Okay. And so that this R plus I omega m minus k by m, this is Zm. And so this line OQ represents Zm. And we consider that this angle is phi. Actually, this is the measure of phase of the impedance. Okay. Now, if you want to find the modulus of this mechanical impedance, you know its modulus will be mod Zm, which I have written simply Zm, and that will be equal to what? This is a square root of r square plus omega m minus k by omega whole square. Okay. And you can see the figure. This phase factor phi will be given by tan phi equal to what? This will be xm divided by r, but xm is omega m minus k by omega. So tan phi will be equal to omega m minus k by omega over r. Okay. So in this way, we have obtained the mechanical impedance of this system and its phase factor. Okay. Now, from this figure, you can see we can express this r, that is the real part, in terms of modulus of Zm and phi. And similarly, we can also define this xm or omega m minus k by omega in terms of Zm. From the figure, it is obvious that if you will write cos phi, that will be equal to this r divided by mod of Zm. So you can see cos phi is equal to r over mod of Zm, and therefore r is equal to Zm cos phi. Okay. And this sin phi, this will be omega m minus k by omega over Zm, and so omega m minus k by omega, this is Zm cos phi. Okay. Now we will substitute these values in the expression for Zm. You know Zm is equal to what? This is r plus I omega m minus k by omega. Okay. But you have seen that this r is equal to Zm cos phi. Okay. And this omega m minus k by omega, this is Zm sin phi. So Zm is a common factor, and you can write this vector Zm is equal to modulus of Zm times cos phi plus I sin phi. But you know cos phi plus I sin phi, this is equal to e to the power I phi. So Zm, this complex impedance, can be written as Zm, that is modulus of Zm times e to the power I phi. Okay. So in the equation where we have defined this complex amplitude A, at the place of this mechanical impedance Zm, now you can write modulus of Zm times e to the power I phi. So you can see A is equal to minus I f naught over omega Zm times e to the power I phi. Okay, and that will be simply equal to minus I f naught e to the power minus I phi over omega Zm. Okay, so in this way we have obtained the unknown constant A, which I have written in the solution, that x of t is equal to A e to the power I omega t. Here A was an arbitrary constant, and you can see I have obtained its value here. Okay. Now after getting this value of A, you can write the solution of that very equation of motion. As you have seen earlier, that this solution x of t, I have written this is A e to the power I omega t. But we have obtained the value of A, which is equal to this much. This is minus I f naught divided by omega Zm times e to the power minus I phi. Okay. So x of t will be equal to this much. Okay. Now combine these two exponential factors and you can see x of t will be equal to minus I f naught over omega Zm times e to the power I omega t minus phi. Okay. Now you can see the applied force under which this motion is taking place. This was f naught e to the power I omega t. So you can say that anytime t, the phase of this force is equal to omega t. This is its phase. But you can see the displacement of the oscillator is given by this equation A1, and at any time t in general, its phase is omega t minus phi, not omega t. So it is obvious that our oscillator oscillates with the same frequency as the frequency of the applied force, but the phase of its oscillation is not same in general as the phase of the applied force. They differ in phase. It means oscillator will oscillate with the frequency of the applied force, but the phase of the oscillator and the phase of the applied driving force, which actually causes this motion, they do not are actually same, but they differ. Okay, so I have mentioned, you can see it is clear that the phase of the oscillator in general is different from the phase of the external periodic force. Okay. Now actually what will be the phase difference between the applied force and the motion of the oscillator? We can actually find it by taking the real and imaginary part of this force. Actually, you know f, which is given by f naught times e to the power I omega t. But e to the power I omega t, you know, this is equal to cos omega t plus I sin omega t. So you can see that this f naught cos omega t, this is actually the real part of this applied periodic force F, and f naught sin omega t, this is actually its imaginary part. So we can discuss the motion of our oscillator by taking either the real part of the applied force or the imaginary part. Okay, we can take. You can see in several books that the original equation of motion has been written either in terms of the real part of the applied force, that is, you can see the book where force will be taken as F equal to f naught cos omega t. And in some other book you will also find that f is taken as f naught sin omega t. Okay, both are periodically varying. But I have taken earlier f equal to f naught e to the power I omega t. Actually, this has been taken for getting the most general result, because when you take f equal to f naught e to the power I omega t, it means you are taking both the real part, that is f naught cos omega t, and the imaginary part f naught sin omega t. Both you are taking. But now for a clear-cut concept, let us take the real part of the applied force and see what type of motion will be executed by the oscillator when we will take f equal to f naught cos omega t, and what will be the phase difference between the applied force and the oscillator. Okay. So now we will take f naught cos omega t at the place of f. Okay. So you can see, since f naught cos omega t, you know this is the real part of the complex function f naught e to the power I omega t. Okay. So in the steady state term will consist only the real part of equation A1. Okay. If we will take this force, see the, sorry, here where is x? X is this much. Okay. Actually, when we will simplify this x of t, you can see this will contain its imaginary part, its real part both. But when you will take force as f naught cos omega t, which is the real part of the applied force, then we will have to find the value of x of t by taking the real part of this equation A1. Okay. And so first of all we will simplify it. So, you know, you have seen that this x of t is equal to minus I f naught by omega zm times e to the power I omega t minus phi. Okay. Now you know this e to the power I omega t minus phi can be written as cos omega t minus phi plus I sin omega t minus phi. Okay. And this factor minus I f naught over omega zm remains at each. Okay. Now let us multiply by this minus I in the terms inside the square bracket. So this will be f naught over omega zm times minus I cos omega t minus phi. And here, when we will multiply this minus I with I in the second term, this will be minus I square, and that will be equal to 1. And so the second term becomes sin omega t minus phi. Okay. So what is the real part of this x of t? You can see its real part will be what? Its real part will be f naught over omega zm times sin omega t minus phi, because the first term contains I. So as I have told you, since we are considering f as f naught cos omega t, and this is actually the real part of the applied periodic force, so we must take the real part of xt for getting the steady state solution. So the steady state solution, when you will take the force like this, will be given by x of t equal to f naught by omega zm times sin omega t minus phi. This will be the solution. Okay. And this is, you can say, this is the particular integral or steady state term. Now x of t can be written like this. This is f naught by omega zm, and you know that sin theta is equal to cos pi by 2 minus theta, or you can also say that this is cos minus pi by 2 minus theta, and this is cos theta minus pi by 2, because you know cos minus theta is also equal to cos theta. So cos pi by 2 minus theta is also equal to cos minus pi by 2 minus theta, which is equal to cos theta minus pi by 2. Okay. So that sine omega t minus phi can be written as cos omega t minus phi minus pi by 2. And therefore, finally we can write x of t equal to f naught over omega zm times cos omega t minus phi plus pi by 2. So this is the steady state solution of the equation of motion of a forced harmonic oscillator when we consider the driving force as f naught cos omega t. In that condition, this is your solution. Now see the phase factor of this x of t and the applied force. You know, the applied force in this case is f naught cos omega t. So at any time t, if I will ask you what is the phase of the applied force, your answer will be it is omega t. Okay. But when I will ask that what is the phase of oscillation of our oscillator at time t, your answer will be omega t minus phi plus pi by 2. So it is obvious that our oscillator and the applied driving force are not oscillating in same phase. Their phase differs by phi plus pi by 2. So phi plus pi by 2 is the phase difference between the applied driving force and the oscillator. Now, since here there is minus sign, so you can say that at a particular time the phase of the oscillator is behind, is lagging to the phase of the driving force. So comparing this equation 11 and 12, we find that in steady state the oscillator lags behind the applied driving force in phase by phi plus pi by 2. Okay. It means force will become maximum, and after some time the displacement of the oscillator will become maximum, because the oscillator is lagging behind the applied force in steady state. Okay. I think you have clearly understand what this calculation, how we can say that during the steady state our oscillator oscillates with same frequency. You can see the frequency of oscillation of the oscillator is omega, and the frequency of oscillation of the driving force is also omega, but their phases are not same. The oscillator is lagging behind in phase from the applied driving force. Okay. Now observing this equation 11, can you say what is the amplitude of oscillation? You know, this factor f naught over omega zm, this is the amplitude. So the amplitude of oscillation in steady state is given by A equal to f naught divided by omega zm. But you have seen that Zm, which is modulus of the complex mechanical impedance, is given by this. This is a square root of r square plus omega m minus k by omega whole square. Okay. So A in this case is given by f naught divided by omega times r square plus omega m minus k by omega whole square, square root. Actually, this is a very important result because in the next lecture you will discuss the problem of amplitude resonance, and you will see at that place we will directly write this expression for the amplitude of the oscillation. Okay. So when we have taken the real part of the applied driving force as the applied force, then you have seen that the oscillator lags behind the applied force in phase by pi plus pi by 2. Actually, you will get the same result if you take not the real part of the applied driving force as the applied force, but you take the its imaginary part. Even then you will see we will get the same result. But how? You can now see. So now let us take the imaginary part, which is f equal to f naught sine omega t, has been applied to our oscillator. So in this condition, in a steady state, if you have to write the solution, you must take the imaginary part of xt. And for this you can see this general result. This x of t is equal to f naught divided by omega zm times minus I cos omega t minus phi. So this term containing this factor minus I, this is the imaginary part of xt. Now since we are considering the imaginary part of the applied driving force, so the solution in a steady state will be written by simply taking this imaginary part. Okay. So what will be x of t in this condition? You can see this will be minus f naught by omega zm times cos omega t minus phi. So you can see I have written it here that in this condition, taking the imaginary part of xt, we have from that equation A2 x of t equal to minus f naught over omega zm times cos omega t minus phi. This is the steady state solution or the particular integral if you write the applied force in this form, f naught sine omega t. Okay. But since in this condition force is in the term of sine function, so let us transform this equation which contains the cosine function in terms of sine function. And you know cos theta is equal to sine theta minus pi by 2. And so we can write x of t is equal to f naught over omega zm times sine omega t minus phi plus pi by 2. Okay. So this is the steady state term when the applied force is taken as f naught sine omega t. Now again compare this applied force ft, which is f naught sine omega t, and this displacement of our oscillator. You can compare. Again you see that at any time t, the phase of the applied driving force is omega t, but the phase of the oscillator is omega t minus phi plus pi by 2. So just like the previous case, in this case too, the phase difference between the oscillator and the applied driving force is phi plus pi by 2. Okay. Where phi, what is phi? I have already defined phi previously. So you can see the meaning of phi there. Okay. So you can see we find that the oscillator lags behind the external driving force in phase by phi plus pi by 2. Okay. Again in this case the amplitude is same. You can see this equation 15. This f naught by omega zm is at the place of amplitude, and also in this case you have seen that f a is equal to f naught by omega zm. So there is no difference in the results when you take the real part of the complex force or its imaginary part. Result will be same. Okay. So amplitude is just like the previous result, A equal to F naught over omega Zm, and you know Zm is equal to a square root of R square plus omega m minus k by omega whole square. Okay. So finally we get that the amplitude in this case is equal to this much. So you have seen how we can obtain the steady state term. Actually, as I have told you that since the complete solution x of t will be given by x1 of t plus x2 of t, where x1 of t, this is actually the transient solution and this is a steady state solution. I have not written here x2, but you can take it as x2, and similarly you can also take it this result, you can take it as x2. Okay. But as I have told you that this x of t contains the factor e to the power minus bt, so it vanishes, it becomes 0, and finally we get xt is simply equal to x2t. Okay, and that's why we simply say that during this motion our oscillator finally oscillates just like a free oscillator. Okay, free oscillator, and its amplitude, the oscillation's amplitude, you can see, depends on the damping coefficient R or resistive constant, and it also depends on the frequency of the applied force. So if we keep the medium constant, so that R will remain constant, but if we vary the frequency of the driving force, then amplitude will vary. And for a particular value of omega, this amplitude A will be maximum. For a particular value of omega, A will be maximum. Actually, when A is maximum, that event is called amplitude resonance. This is a very important problem of oscillation. But that amplitude resonance we will discuss in the next video. So I have written here, in next video we will get the concept of amplitude resonance. We will actually see for what value of omega this A will be maximum. Okay, and what is the maximum value of A. All these things we will discuss in the heading amplitude resonance. Okay. So I think the concept which I have discussed in this lecture is now definitely clear to you. So watch the video seriously, write down these things in your notebook and revise it. Definitely you will be very happy that you know everything which I have taught. Okay. Thank you very much.